Namaskar, welcome back. So, today we are going to start with a new topic. But before we get into that, I'll just try to browse through what we have discussed about the two different environments. That was one was your extensional environment, and second is your compressional. Now, in this, we also discussed very quickly. I'll just put here that if you have an faulting which is taking place, so you have an extension here which is going on, and then if there is a fault here, then the scarp which you will see will be something like this. Okay, scarp formation, and then after erosion, you will see a topography like this. Okay, that is the stabilization of the scarp and all that. And second one was, so this is your extension, this is your compression. So in compression we have again that you have deformation, but this is, you have sigma 1 here, and suppose there is a fault here, then this block will move up, and in this case this block will move down. Okay. Now in this case what we see is, suppose we have an high angle faulting, or if you say a sort of an low angle, then after the erosion, so this is your thrust fault and this is your reverse fault. Now after the erosion, what you will see, the topography will be something like this. Okay. So point is that the topography remains very much similar to the normal fault and the in the reverse fault or compressional tectonic environment. So in this case, if you see this in 3 dimension, then it will look something like this. Okay. So we have a topography here. So and fault displacement has taken place over here. Okay. So to see the section here, what we will do is that we will open up a trench in this portion. Okay. So this is the area where we will put the trench. Okay. And this trench is for the paleoseismic studies. And in case of the normal faulting also, if you put this in 3 dimension, then you will see that the topography is more or less similar, and you are going to put your trench in a very similar way, that is transverse to the your fault trace. Okay. So almost the fault is over here, so you will try to see the section. Now coming to the other part. Okay, that is the last topic in terms of the tectonic environments. Okay, we have the third one is your strike slip. Now before I move to the strike slip environment, I'll just like to uh, uh, mention here that coming to the third uh, portion of the tectonic environment, and that is your strike slip environment. So before moving to the in detail, I would like to mention few things which are important, that in this case mostly we see an horizontal movement. The block is moving towards us or away from us. Okay. So if you put a block here, so suppose you have the section here, and there is a fault which is passing through this one. Okay. And in section you have the fault here. Now if the block is moving away from us, or we say towards us, then that will be your, so if the right block is moving towards us, then we term this as a right lateral strike slip. Okay. So if this is the scenario, then the block is moving towards us, and this right block is moving towards us, and this is moving away from us. Okay. So this we will call right lateral strike slip fault. Okay. and if it is opposite, then we term this as an left lateral slip. Okay. So, if this is moving away from us, this has moved away and this is moving towards us. So, this will be your left lateral strike slip faulting. So, with this understanding, we will move ahead. Of course, one more point is that uh, of the scarp which will be developed if there is an oblique slip. Okay, if there is a component of normal along with this strike slip or reverse along with this strike slip, then you will also see a scarp very much similar to what we see in the normal and reverse faulting environment. So, in this case also we put the trench across this to understand the deformation. Okay. So, basically this exercise of the paleoseismic trenching will let you know, one, the subsurface geometry of faulting. Second is the past history of paleo earthquakes. So, these are the two important part, and what is the, even you can talk about then the recurrence, say even the slip rate, what was the slip during single event. Then you can talk about the recurrence interval between the two earthquakes, that you can and, extract this information from trenching. Okay. So, let us move to the strike slip environment and see what are the details for that. Okay. So, strike slip faulting environment, as we have discussed, that we will mainly look for your right lateral and left lateral strike slip movement. Which are the areas on this planet which shows us the strike slip environment? Okay. So, mostly most common is your spreading centers, but they are not like triggering large magnitude earthquakes, but there are few areas which are like quite dangerous in the sense, like one is between the Pacific plate and the North American plate, where we have the San Andreas fault system, and there are few locations where there is an strike slip in Himalayas also, in the frontal portion also, that is within the wedge, and also we have a major strike slip, that is your Karakoram fault system. And on either side of in the Indian plate, we are also having a strike slip faulting environment. For example, if you look at the eastern side, you have a right lateral strike slip going on the western side you have left lateral strike slip going on, and which is well manifested by your Sagain fault system, and you have in the east, and in the west you have your Chaman fault system. So, these are the areas where you have an strong strike slip motion which is going on, and which has resulted, these areas have resulted into major earthquakes in the past. Okay. So, basically we are looking at the lateral slip of along the fault, and if we say along the fault, then we are looking at the strike slip along the strike. Okay. The two other environments which we have discussed is the normal and the reverse, that those are the dip slip faults. Actually, they move along the dip, and if you have an oblique, then you have strike as well as dip slip faults. The whole combination of both you can see at say several locations. So, geomorphic markers associated with the strike slip faulting environment, uh, how we will identify, that we will discuss, and what are the parameters, or we can say the landforms we should look for and towards the identification of this strike slip faults on surface. Okay. So, major strike slip faults that have been assessed for paleoseismicity are typically associated with plate boundaries. Okay. And that what I was talking about, that this is between the North American plate and the Eurasian Pacific plate. Okay. So, North American and Pacific plate, if you see, then you have an uh, uh, San Andreas fault system, which is one of the most deadliest. Okay. Then there is another one between Caribbean and North American plates, that is your Mutagao fault and Alpine fault in New Zealand, Dead Sea transform fault in between the African and Arabian plates. Okay. So, these are some few major fault systems which exist. Of course, if you ask, then there is few more in Asia, in Central Asia, and even in Japan. Okay. Median tectonic line, and the earthquake of 1995 was on a strike slip fault. Okay. But there was a component of reverse faulting also in that. So, and as I mentioned, that there is a Karakoram fault system is there, and also the Sagain fault system, which resulted into a recent major earthquake in that area. Okay. So, there we can classify this as in conservative plate boundaries, and these are the transform faults at oceanic plate boundaries, a mid Atlantic ridge or mid oceanic ridge, where the spreading center is basically seen. Okay. And then transform faults at continental plate boundaries, basin and ranges, they will result into the formation of that. Okay. Then there is passive margins, which is along Bay of Biscay, and then destructive plate boundaries with oblique convergence. Okay. So, these are seen along New Zealand, California, Sumatra, Andaman subduction zones. These are all destructive plate boundaries where convergence is going on, but the convergence is oblique. Okay. So, that has a component of compression plus your strike slip. So, this is these are the, and we have the recent earthquake, not very recent, but of course in 2004 was the major earthquake in this region, and even in the major earthquake was in Japan. Okay. And that is again we are having a strike slip motion in that region. Okay. Then constructive plate boundaries, mostly we look at the back arc basins. Okay. Which are seen in subduction zone areas which are behind the ridge line of and that can be also seen in our region like Andaman Nicobar region also. Okay. Then within the plate also we can have the strike slip fault, and one of the good example which we can take up, that is in combination of your Karakoram fault system, and then you have other fault system which are developed in Tibetan region, and that is facilitating the escape of this the Tibetan plate towards south. Okay. South, we can say southeast. So, that escape is also facilitated by major strike slip faults like Karakoram fault, then you have Altintek fault, Kulun fault. So, these are the fault systems which are seen having strike slip motion in to the north of Himalayas. Okay. Then transtension mid Atlantic ridges we can see. So, if you look at the transform zones in the areas of spreading centers. Okay. So, it looks something like this. Okay. So, you have this one is your uh, South America, this is your North America. Okay. And you have a mid Atlantic ridge, which is, and this is Africa, and then India is so you have here. Okay. So, that is in Tibet inside here and all that. Okay. So, this block is actually moving towards this side. We may be having one slide where I will just show, and probably most likely I have shown you before also. Okay. So, this is a such scenario in the transform zones where we see clearly that the shifting of the ridge, okay, and this shifting of the ridge, you can say that this is because of the spreading centers, okay, and along the fracture lines they are moving apart, okay. So, this the ridge are the same piercing point where you can see, but of course this has moved this much, okay, but the motion here is because this is typical spring centers, these are moving in this direction, okay. The plates are uh, up, like uh, we can say that they are in extension and they are moving away from one another because of the along the movement along the fracture zone. So, again on if you see the section, that is what I was explaining, that these are the spreading centers which we call mid oceanic ridges where younger crusts are formed, okay. And as you move from away from the this spreading centers, you see that this crust will are the older ones, okay. So, as I told that over the time you can also look at that how much movement has occurred, okay. So, for example, the mid oceanic ridges and then inactive fractures, because these are not active, these are just facilitating the movement, okay, but they are not very active on the other side, okay. So, the active zone will be only in the area where you have the two piercing points, okay, of the ridge line, okay. So, this is the area which is, we can say that this is an active fracture zone and the other part is the inactive fracture zone, okay. And that what again we have discussed, that as you move away, then this will be the older plates, okay, and this side you will be having the younger plate which has been developing. So, overall this is the amount of displacement which has been marked here. So, if you try to look at uh, the the total displacement in terms in time, then you have, for example, the crust formed between time 1 and 2, then you can see that what was the movement exactly, okay. So, this is further displacement of that, but on surface if we have to see, then what we should look for is some sort of a reference point in terms of the landforms or the drainage systems we can look. And this is the example from 1979 Imperial fault earthquake from US, which shows the displacement of the agricultural boundaries, okay. So, if you try to look at this clearly, this portion comes here, whereas this portion comes on this side over here, okay. So, is same, okay, fine, here also it is, this is the piercing point. So, the this portion has moved like this, okay, and this has moved over like in this direction. So, if you look at, then this becomes your left lateral strike slip fault, okay. Now, strike slip faults, as we have discussed, that you will see a two sort of an motion movement, sense of movement. One is the right lateral if the block is moving towards you, and that is termed as dextral slip movement, okay. So, this is one like term which has been used for your right lateral strike slip, whereas for left lateral strike slip, when your left block is moving towards us, then we say that as an sinistral moment, okay. So, if we try to look at in terms of with the reference with the landforms, okay, or the drainage, then how it looks like is that you have a drainage which is flowing from here and then deflected along the fault. Similarly, over here along the B fault and the C fault, okay. So, this is typical of like the stream earlier was flowing, for example, you say that the stream was flowing like this and there is a fault along this line, and if this fault has a tendency which will result into the right lateral strike slip, So, this portion is coming towards us, this is moving away, then you will see sort of a drainage which is getting deflected along this line. Okay. So, this goes like this and you will see a sort of a deflection along the fault. Okay. So, you have this fault is sitting here and you have a deflection. So, this is a typical way of identifying strike slip fault using high resolution satellite data. Okay. Now, if we take the man-made structures, then if you have a right lateral, then the dextral slip, then how it looks like, and if you have a sinistral, then how it looks like. Okay, that is already we have discussed. Okay, so let us move further and see what uh, evidence or the signatures we see on the surface. That is the manifestation of your strike slip moment. So, as I told that this is one of the deadliest fault system on this planet, and that is San Andreas fault system, which is formed because of the oblique convergence between the North American plate and Pacific plate. So, in this photograph on the right hand side, that is an aerial photograph, oblique aerial photograph, what we are able to see is one is very prominent uh, shifting of the channels. Okay. So, if you see this one here, then this channel is over here. Of course, this one can say that why not this actually, but based on the erosion what we see here and the valley width and all that, it has been marked that this is the connecting stream which used to flow over here in past. Okay. So, this has moved right laterally again the because as we have discussed in the previous one, this is the block has moved towards us, okay, and this has moved away. Now, along with this, what you see is a very typical topography here, okay, and that is what we call as in fault scarp. This is your fault scarp. Okay. And the fault trace, if you have to mark, this is your fault trace which goes here. Now, one thing which I will mention here and that we will recall when we are talking about the sense of movement or the amount of movement we are talking about. So, what you will be able to uh, observe here is that the other streams are also offsetted, but the offset is not as much as what we see over here. Okay. So, this is also going like this, this is also okay. So, maximum offset of the stream is this one. Okay. So, this is showing your maximum offset, whereas the streams are showing minimum. That means that this fault has remained active since long, and what we see the displacement, the amount of displacement of this stream is cumulative displacement. Okay. Let us move further and see more examples. This was from 1960 San Francisco earthquake, where the man-made structure, okay, this is a fencing which moved along this line. Okay. So, this is your fault line along which, and this is a part of the San Andreas fault system. Okay. So, this block has moved this side and this has moved away. Okay. So, that shows that again if you see from here, okay, this shows an right lateral strike slip. Okay. Similarly, on the other figure, it has been shown that you will come across, if you are having strike slip, looking at the strike slip, then you will come across like linear valleys, okay, offset of streams, formation of sag ponds, and one more thing which we will talk about. So, there are you will be able to see a formation of ponds along this uh, along the strike slip faults. Okay. And streams, if you carefully look at here, that has been shown, there is a stream here which goes and flows through this. Okay. So, you have streams which are offsetted, because of the strike slip. Along with this, the sag ponds, we will also come across pressure ridges. Okay. So this we will discuss in coming slides and coming lectures. Okay, that how the sag ponds are formed, and in the same area along the fault, how this ridges are also formed. Okay. So this is again you have a right lateral strike slip, and as I told that you can see the main is the even the ridges, if they exist in that area, will also get shifted or offset will be seen. Okay, there. So few are like most common, and I would say most important features you will come across will be your linear ridges. One, second is your sag ponds. Okay, offset of drainage. Then also you will see in formation of scarps, and linear valleys as well as linear ridges you will see. Okay. And this is what I was talking about, the pressure ridges, or we also call this as an shutter ridge. Okay. So these are features which you will come across a typical strike slip faults. Okay. So section you will see that this fault trace is almost like vertical, or you will see a sort of branching out faults coming up, and that we will learn that how we term and how we will try to differentiate between that, whether there is, and because when you say that there is a formation of the sag pond is a basin type feature. Okay, so it will be a basin. So how extension is taking place along the strike slip, and when you say pressure ridge, then the compressional tectonic portion is there, or maybe the component is there. So that we will try to understand in coming slides. Okay. Now there are few examples along the San Andreas fault system, which shows that the faults within the one of the fault is creeping. Okay, so it keeps on moving very slowly, and that was observed uh, by the people who have their houses on sitting exactly on the fault line. Okay, and beside the house also they come across this typical way of shift. Okay, so the faulting is over here, and that has shifted the uh, the the water drain. Okay, so this fault is the Hayward fault is a part of the San Andreas fault system. This all falls under the San Andreas fault system, but they slip at different rate. Okay, and this I think if I remember that we discussed in very beginning, where we were talking about the concept of the earthquake, and the example which was been given, that if you take an playing card bunch and then try to shift applying pressure. Okay, then you will see that the movement along the cards. Okay, different cards which marks the boundaries, which will that will not move very fast. Okay, so that has a tendency that they will move at different pace. Okay, and that exactly what has been seen here, that on the margin side this slip is higher as compared to if you move the internal side. Okay, so this is the Hayward fault part, which is creeping. Okay, so I'll stop here, and we'll continue with the next in the next lecture. We'll discuss more on the fault strike slip fault system, and story I will tell about your this uh, San Andreas and Hayward fault system. Okay, till then, thank you so much. Namaskar.